Today we will study homogeneous higher order linear differential equation with constant coefficients. So in the last video we have studied reduction of order, that is also for second order linear differential equation that is homogeneous, and if one solution is given then you have to find out another solution with the reduction of order. So word to word I am giving you the example of this homogeneous. We have a higher order differential equation. Now we are dealing with the higher order differential equation, and that is an, these are coefficient, into d and y divided by dx to the power n plus a n minus 1 into derivative of n minus 1th order to so on. I'm writing it in the descending order. You can also write it in the ascending order. To so on, plus a2 second derivative d2y by dx square plus a1 dy by dx first derivative plus a naught into y equals to 0. So these all are an minus 1, a2, a1, a naught. These all are coefficients. Okay. And that is equal to 0. So that means this differential equation is homogeneous. Okay. Higher order means that it is more than we are dealing with more than first order derivatives. So that means higher order derivative that is related to this generalized form, that is n. And linear differential equation means that these coefficient functions, again the properties of linearity, that means first condition is all these coefficient functions must be, the scalar functions must be some constant function or dependent, it depends on an independent variable. Second condition is that all y's and all the derivatives of y should have degree 1. So you can definitely see that all the y and derivatives, higher derivatives of y has degree 1. And third condition is not applicable here because it is homogeneous. So g of x, we don't have any concern with the g of x because here it is 0. If it is non-zero, then we can use some other kind of techniques with constant coefficients. So okay, this linear condition is met here. Constant coefficients means that all the scalar functions like an, this an minus 1, a2, a1, a naught, these all must be some constants, right? So this method is applicable for homogeneous higher order linear differential equation with constant coefficients. All right, so we want to judge that which type of solution is for the higher order, because first order linear equation we know that how to find the solution either with the separation of variables or with some exact equation, homogeneous equation with some integrating factor method and all that. But with the higher order differential equation, how to deal with that? So in this lecture we will study this type of method. So first of all, first order linear differential equation is of the type, for example, we have I restrict this general nth order differential equation to this first order differential equation, and that is dy by dx plus a here is a constant, a into y equals to 0. So either you can solve it with the integrating factor or you can solve it with the separation of variables. So I am using the technique of separation of variables or separable variables. Then what will be the solution? Dy by dx minus a into y. So 1 by y dy minus a into dx. Okay. Integrating both sides, 1 into dx, natural log of y equals to minus a x plus c. So y equals to e to the power minus ax plus c. So if I split these values, it becomes e to the power minus ax into e to the power c. I call it as c1. So solution is y equals to c1 e to the power minus ax. So this is the solution of first order spellings are not right, order linear differential equation, right? So I suppose, and I generalize it, that all the higher order derivatives should be, if I extend this to second order differential equation, then the solution should be c1 e to the power minus ax plus c2 e to the power minus some other constant into x. So that means in second order the solutions are of basically linear combination of two variables. Simply, if I go further, if I deal with third order derivative, then the solution will be c1 into e to the power some function plus c2 into e to the power some function plus c3 into so three linear combination of three constant and functions. So this is all about this. We generalize it. So that means that all the higher order derivatives, all the solutions are of exponential basically exponential functions and constructed out of the exponential functions, right? So we can say that all solutions are basically exponential functions or constructed out of exponential functions. Okay, now I will consider the second order linear differential equation, and I'm writing it as with the constant coefficients. So second order is d2y by dx square, and now I am writing, instead of an minus 1, a2, a1, a0, I am writing simply a, b, c, which is three of these are constants: a into d2y by dx square plus b into dy by dx plus c into y equals to 0. Now we are dealing with this second order linear homogeneous differential equation. Okay, we move to our next page. So in the last page we have generalized that all the solutions are of the type of exponential functions. So if we have second order differential equation, I'm writing it again, that is a into y double dash plus b into y dash plus c into y equals to 0. If we have this type of function, then the solution should be y equals to some e to the power exponential function. So if we in this first order we have minus a means this minus a means some constant. So I generalize it and we say that if it is the solution of this differential equation, now what we do, we differentiate it and it becomes m e to the power mx, and I differentiate it again and that becomes m square e to the power mx. Now I put these values, I mentioned this equation 1 and I put these values in equation 1. It becomes standard y double dash has value m square e to the power mx plus b is y dash is this m e to the power mx plus c, and y is e to the power mx equals to 0. Alright, in these three terms you can definitely see that am square e to the power mx plus b m e to the power mx plus c e to the power mx equals to 0. So you can definitely see that e to the power mx is common here, and rest of the terms becomes am square plus bm plus c equals to 0. And these two are the products that we can say that either e to the power mx equals to 0 or am square plus bm plus c equals to 0. As you can definitely understand this thing, that e to the power something can never be equal to 0 if it is a negative quantity. If it is a 0, the power is 0, it can never be equal to 0 ever. Exponential function can never be equal to 0. So that means this term is equal to 0. And you can definitely see that this term is, which type of equation is this? Think about it. Which type of equation is this? It's basically second order equation. M is variable here, or M is some yes, variable, you can definitely say. So M is, this equation is basically, this equation is basically quadratic equation, and this equation here is called auxiliary equation, or we can also say characteristic equation. Based on this equation we decide the solution types, right? So in the next video we will study the cases of the solutions, that how solutions arises from this second order, based on the nature of this second order differential equation, how this its solution is arised.